Welcome to The Explainer. Today, we are tackling a really common and honestly a pretty costly industry assumption. The idea that you can just take the exact same cable management system you use indoors and slap it outside. Well, if you've ever assumed a simple copy-paste works, you are definitely going to want to rethink your next engineering project after this.
Right off the bat, our source material hits us with this stark reality. Same tray, different location is rarely a neutral choice. I mean, this completely shatters the idea that cable trays are just interchangeable across all environments. Look, there's this really dangerous habit in procurement and engineering where folks just copy-paste an indoor spec for an outdoor run. But taking that exact same piece of metal and putting it in a completely different environment, that fundamentally changes how the system behaves, how it degrades, and ultimately whether it even survives.
So this naturally leads us to a pretty big question, right? If we can't just copy and paste an indoor system to the outside, what exactly needs our attention? What are those hidden variables that engineers and project managers always seem to miss until it's literally too late? Well, here is our roadmap to figure that out. We'll start with the indoor versus outdoor contrast, look at what actually changes first, talk about the big support spacing shift, dive deep into why transition zones fail, and finally, how to specify the right system.
All right, let's jump straight into point number 1, the indoor versus outdoor contrast.
To really get this, let's compare the two. Imagine a pristine, dry electrical room indoors. It's temperature controlled, there's zero precipitation, no UV radiation baking it all day. It's a highly predictable space. Now, contrast that with a blistering commercial roof or an exposed industrial pipe rack outdoors. Out there, your cable tray is fighting a daily war against driving rain, pooling water, corrosive salt air, massive temperature swings, and direct, intense sunlight. The contrast literally could not be more extreme. And because of that, the physical demands on our hardware are fundamentally different.
Moving on to our second point, what actually changes first when we move outside?
Now, here's the crucial thing to understand. The physical width holding the cables, that actually stays the exact same because your cable volume hasn't changed. But everything protecting those cables must fundamentally shift. You see, people often assume outdoor just means bigger, but it actually means tougher. Out there, severe wind gusts can turn a poorly covered tray into a literal sail, ripping it right off its mounts. No joke. So your material might need to instantly shift from standard galvanized steel to, say, marine-grade stainless, or even fiberglass reinforced plastic. And your cover strategy? Well, indoors, you might have an open ladder tray just for ventilation, but outdoors, you instantly need peaked covers to shed water and protect against debris. The whole defense mechanism has to adapt immediately. And that adaptation brings us to our third section, the support spacing shift. Just look at the numbers here. In a standard indoor setup, engineers routinely space their support brackets out at 3.0 meters apart. But the absolute second that tray goes outside, the span often needs to shorten dramatically. We're talking down to just 2.0 or 2.5 meters. So why the sudden shrinkage? Well, this reduction isn't just random guesswork. It is physically forced by two main things. First, the addition of those required protective covers we just talked about. That adds some serious deadweight to the tray system. Second, you have the introduction of completely new environmental loads. Outdoors, your tray isn't just holding cables anymore. Suddenly, it's holding a heavy blanket of winter snow, or it's catching severe wind gusts. If you try to leave your supports at 3.0 meters under those brutal conditions, the metal is going to bow, fatigue, and eventually fail for sure. Which leads us perfectly into section 4, and this is a really big one. Why transition zones fail. Before we talk about why they fail, let's define what a transition zone actually is. It's the specific point where a cable route exits an indoor environment and enters an outdoor environment. It is absolutely critical to think of this area not just as a continuous piece of metal, but as a violent clash between two completely different atmospheres. It's literally the hole in the wall where your safe, controlled indoor climate slams right into harsh outdoor reality. And the source material specifically points out that these transition zones fail way more often than straight sections. Why is that? Because it's the exact spot where professionals tend to forget to reconcile the two environments. First off, you have a brutal clash of exposure conditions. Picture hot, humid indoor air rushing out and hitting freezing cold outdoor metal. Boom! Condensation builds up instantly. Second, you get improper cover type transitions. Imagine an indoor open tray suddenly meeting an outdoor covered tray. If that's not sealed correctly, it acts exactly like a funnel. Which leads us to the third and probably most destructive point, inadequate or entirely missing drainage setups.
If water runs down an outdoor covered tray and hits a poorly designed transition zone without proper drainage, it will literally pour right back inside your building or just pool up and cause rapid localized corrosion. It's an absolute disaster waiting to happen.
So, how do we fix this? That brings us to our fifth and final section, specifying the right system. It really comes down to reversing how we normally plan these things. By following these exact steps from the source, we can basically bulletproof the design. Step 1, check the transition zone first. Don't plan all your long street runs first. Start by solving the hardest part. Step 2, accurately match your material and cover type to the actual outdoor exposure, not just some generic baseline. And step 3, verify your drainage setup at that exact junction, making sure water escapes the system long before it ever has a chance to enter your facility. To put all of this into a practical context, let's look at how the industry is actively solving this. Manufacturers like Xinma, for instance, engineer specialized solutions to handle these specific shifts. As you can see, they adhere to rigorous standards like IEC, NEMA, and British standards. And look, these aren't just fancy acronyms. They are intense testing protocols. They ensure that when a system is deployed in super demanding sectors, like data centers, rail transit, or massive industrial plants, the materials and the transition geometries can actually withstand both the indoor requirements and those brutal outdoor loads, all without compromising your critical cable infrastructure.
So I'm going to leave you to ponder this final question as you evaluate your next installation. If transition zones really are the weakest link, is your current specification leaving your outdoor route exposed from day one? Because as we've learned today, getting the transition right, accounting for those heavy environmental loads, and recognizing that going outside literally changes everything, well, that's the only real way to ensure your whole system actually survives. Thanks so much for joining me on this explainer, and I really hope this helps you specify smarter, safer systems moving forward. See you next time.